is a member of the technical support group, and he is our webinar coordinator. And we are keeping the same format as always, so meaning that if you have any questions during the webinar, please use the questions panel. I will be monitoring the questions throughout the webinar, and we will have a short Q&A session at the end. If we don't have time to answer all of the questions, we will get back to you by email. And yes, this webinar is being recorded, so it will be available for later viewing. Roberto, it's all yours.
Thank you, Carol. Whether you need to get a complete coverage of your part while scanning, or you simply need to reach measurements that are beyond the range of your device, combining data from multiple device positions is a common task for metrologists. This webinar will present the recommended workflows as well as the tools available in PolyWorks to efficiently and accurately perform this task in your day-to-day operations. The need to work with multiple device positions originates from a very simple challenge, which is not being able to reach all the measurements you need from a single device position. This can be because we're measuring large parts with a portable arm, or because of line of sight constraints when using optical tracking devices or laser trackers. In this example, we have a leading edge assembly fixture for which the following measurements need to be inspected. We have the features required for a plane axis center point alignment, additional features located on the rib number 1 and rib number 5, which are located at both ends of the part. We have a distance between some of those measurements, as well as some comparison points located on the back of rib number 5. To measure all of this, we're going to use a 1.5 meter arm located in the blue device position, and which can only reach the measurements in the area highlighted in blue. So in order to get all the measurements required, we are going to need to move the device to a second position, which will extend our range into the area highlighted in red. And this area in red is the one you see on the right-hand side of the picture. The key here is going to be being able to measure from both device positions and keep the data that we acquire aligned to each other to create a consistent data set. To achieve all of this, we are going to be using device position targets, which are point-reducible features located in areas common to both device positions. Our inspection will start in this project with our device located in the blue position, or position number 1, and already aligned to the CAD model of the fixture using a surface points alignment. Note that alignment to CAD is an optional step and that no CAD model is required for the operations that will follow. Since we know we will eventually move the device to a second position, it is a good practice to start by defining our device position targets before we take any measurements. Having them defined will give our project a reference that we can return to at any time if for some reason the device or the part moves or something else changes in our setup. This is even a good practice for single device position projects that might take a long time to measure or will be completed in different stints, since we can use the targets to realign our device to our previous measurements at any time. We can define our targets by using the button available to that end in our device position toolbar. And from here, we can probe 3 types of targets. Before probing the targets, let me hide the CAD model, since I will be using the PolyWorks virtual probe on the blue data object that you see on the screen, which represents the area that we can reach from device position 1. The first type of target that we can probe, it's uncompensated points. And this is the most common type of target that is used for this operation. And the reason for that is that you only need a single point in order to acquire them. And they are typically holes smaller than the probe, like the one you see here in this example, but they can also be conically shaped artifacts specifically designed for this task that can be added to your part, like the ones you see on the screen. The important thing is that when probing them, the probe center will remain in the same location regardless of how you probe that particular point. It is also possible to probe circles as targets. And in that case, when you probe the circles, the center of the circle or the resulting circle will be the one that will be used as the device position target. The final type of target that we can use are spherical targets. And here the same principle applies. I'll probe a normal sphere, and the center of the sphere will be created as a target in my device position plane. Note that in all of the scenarios, in fact, none of the features that we have probed will be added to the tree view, since most of the time they are only needed for the move device operation and do not need to be inspected. Also, when deciding where to position our targets or which targets to use, it is important to try to have them cover a large volume, even larger than the part we're measuring if possible, like shown in the image right here. It is also important to avoid positioning your targets in a collinear setup, since this might cause some alignment issues. Another question we get asked all the time is, how many targets should we use, or how many targets should I use for my project? And even though 3 is the minimum number of targets required mathematically, most people will use between 5 and 9 targets, which provides flexibility in case some of the targets move or are no longer reachable from your device position. With our targets now properly defined, we can proceed with the measurement of all the features required for our inspection that can be reached from position number 1. I'll start with my primary alignment plane. And you will note that I cannot actually reach all of it from device position 1. So I will still probe it, and I will make sure to probe as much as I can from this position, and we will continue its measurement once we have moved the device to the second position. From position 1, we can also reach our front circle, as well as the features located on the front rib, number 1. So I'll go ahead and probe those. For the circles, we have inserted a 1/2 inch pin in order to facilitate its probing. And in this case, the front plane or the front rib plane is also the constraining plane for the circle that is located here. At this point, I have completed the measurements that I could reach from position 1, and it's time to move the device to our second position to complete the inspection. We will need to physically move the device to the right, which will result in our measurements no longer being aligned to the measurements we did in position number 1. We'll also need to click on Move Device to notify the software that we have physically moved the device to the second position. And here, we can specify in the options that we will be using targets as the alignment method to align to our previous device position. As soon as this is done, we can start probing our targets from our second device position. And you will know that I can actually probe targets in any order. It's not necessarily for you to identify them. You can simply probe them in any order. All right, wait just 1 second. All right, so I have probed my first spherical target. And I will continue now with my point reducible targets. And as soon as 3 common targets have been probed with the previous device position, our device position will now align to the previous device position, as you can see here. And at this point, I can continue to probe additional targets, common to the position that I probed before, or even add new targets to prepare for a future device position. In this case, I will probe one of my remaining circle targets. And you will know that as I probe a fourth target, that the deviation calculated for the targets on the list will be updated, since every time a new matching target is added, we recompute the alignment and update the results. Once the probing of my targets is completed, I can use the device position targets pane to review my alignment statistics. Here, we can see the different deviation for each one of the targets, as well as the maximum deviation for each device position. From here, we can also remove targets, which will automatically update our device position alignment. And once we're satisfied with the alignment, I can continue my inspection from position 2. I will begin by adding probe points to my primary alignment plane to complete its measurement. And then move over to the right side to continue our measurements. In this case, for the front circle, number 2, as well as the rib 5 features. Once again, we have a pin here that will help us better measure that circle. And we can probe our plane and our circle as well. To complete the inspection, I will need to probe the comparison points that are located on the back end of rib number 5, and that can only be reached from this device position. Now that this is done, we have completed our inspection using our 2 device positions to get measurements that were beyond the range of a single device position for this particular device. It is important to note that when working with multiple device positions, it's all about aligning data from one position to the other to keep one consistent data set. And all of this regardless of the alignment to the CAD model, which is a separate and independent operation. This will become even more obvious in our next scenario, in which our goal is to get front and back coverage of a part while scanning. This is a very common task in reverse engineering applications, but also in inspection, especially for cylindrical parts or when analyzing part thickness or 2D section profiles. In this case, we are going to be scanning the plastic shell of an electric drill, for which we need enough coverage to analyze its thickness, especially in the bottom portion. And since we have no fixture to scan it from a single position, or to scan everything from a single position, we will simply scan it by putting it on the table and scanning it from the yellow position first. And then we're just going to turn it around, put it on the table again, and scan it from the green position to eventually combine those 2 scans into a single object that we can use for analysis. Let's start with our first scan right away. And as I said, we position the part on the table, and we're getting as much as we can from the front. And since we know we will be combining this scan with another one at the end of our workflow, we can use the point cloud from mesh data type as our final data type. So we can save some time by postponing the mesh finalization process. So I finished scanning that first portion of the part, and we are now ready to lay it on the table from the other side and complete the scanning. However, before we can start scanning, we need to create a new device position, much like we did before, to specify that we have moved the part to a different location. This time, however, we will not use targets for our alignment. Instead, we will choose custom as the alignment method. All this means is that we will be able to align our two device positions to each other using any of the alignment techniques offered by PolyWorks Inspector. I can now proceed to my second scan. And as expected, it is not aligned to the previous one since I just moved it to a different position in the table. And I will try to get as much as I can from that back side of the part that I couldn't get before. But I will also try to get some overlapping data in this top portion right here, as we can see in this particular scan path, since overlapping data is what will allow us to align the two scans to each other. So I'm done with my scan now. And we now have two independent surface scans in our tree view. And in order to align them, we're going to be using a best fit data to data objects alignment, which was designed specifically for this scenario. Here, we need to choose which scan we're going to be aligning to which, and we can do that from the corresponding drop-down boxes. In this case, we're aligning surface scan number 2, or the green scan, to the yellow one. And by starting, we're going to be put in a split mode where we're going to need to perform a point pairs pre-alignment. And by picking our points and launching the alignment, we now have our two scans aligned to each other. Note that for both this scenario and the one with targets that we saw earlier, we can repeat the steps multiple times if more device positions are needed to achieve our results. In this case, for example, I could add a third scan and align it to the first two, repeating the same steps that we just saw. However, for efficiency and accuracy, it's typically recommended to try to complete our task with as few device positions as possible. The final step for this workflow is to simply combine the two scans into a single data object or into a single polygonal mesh. And after this is done, we are going to be able to export this single data object out of PolyWorks for use in downstream applications if that's where we're doing the analysis. Or we can simply use that object that we generated to do the thickness analysis I mentioned in the beginning by, for example, using our thickness color map tool and adding some annotations to highlight the deviation in some of the key areas at the bottom of our part. We have now seen the two main workflows that allow you to measure parts using multiple device positions. However, other scenarios are also possible. You could use targets to align two sets of scan data to each other, or use the custom method to use a feature-based alignment when no targets or point-reducible features are easily available. Regardless of the scenario, PolyWorks Metrology Suite offers the tools you need for the task of measuring parts using multiple device positions.
Thank you, Roberto. We have a number of questions that are coming in, so let's try to have a few ones in there. The first one is regarding reporting. So is it possible to put the results of the alignment, the device move alignment, into a report?
Okay, so I'm assuming the question refers to the alignment we did for with targets.
Yes.
If that's the case, we can go to the Manage Device Positions and Targets pane where we were able to see the deviations while we were working. And it is not only possible to see the deviations from there, you can actually also create a report table from there. There's a couple of options there, but basically this will create a report table that will be sent to your formatted report, and where we will see the targets and the deviation for each position as well as an RMS deviation. It would be also possible to do it in the scanning scenario. In this case, you will need to report, remember the scanning scenario we were using custom, so we were simply using a typical alignment from PolyWorks. So you will report this the same way you report any of the other alignments in PolyWorks.
Thank you. Second question, regarding targets. So we probe targets, or that's the first example that you showed. Is it possible to use existing features as targets instead?
That's a good question. It is possible to do it. Most of the time you will not need to if you follow the kind of the classic workflows that we just saw here. But it is possible to do it. From the definition of targets, I've chosen the probe method, which is the most typically used one. But if your targets are actually features that you also use for inspection, you can use the from primitive center method, which allows you to select any feature in the tree. For example, let me zoom into my front rib circle 5 here, and define a target right at the center of that. It's used in some more advanced scenarios, but in a classic workflow, it's not necessarily the way that I would recommend you to go, since it would require you to probe that circle from the second position as well. So it might create some duplicate information in your project.
Okay, and we're going to throw in one last question in here. So when you do the scan-to-scan alignment and you pick some points, some point pairs, how close do they have to be? So we have a threshold?
All they need to do is they need to form an approximately the same shape in space. What I mean by that is, and let me put myself into that mode so you can see it again. So all you need to do is get them to be approximately in the same shape. And you saw that I actually did it very, very quickly and not very precisely, because all that matters is that 1 corresponds to 1, 2 corresponds to 2, and 3 corresponds to 3. And in this case, they kind of form a kind of an L shape, more or less in the same area. It's just a starting point. So your alignment is then going to take over and do a bunch of iterations to really align each scan to each other using every single point. So it's not very important that you're that you're very precise with it. And as you just saw, I can even redo it if I find that the first time I did it doesn't work.
Perfect. Thank you, Roberto. And this is all the time that we have for the questions. I see that a lot of them are coming in, but don't worry, we'll get back to you by email. This webinar has been recorded. It will be available on the Innovametric software website. Now be careful, we are restructuring the website. The webinars are now found under the About Us tab. So you will have to navigate to the About Us section, then access webinars, and you will find the collection of webinar recordings that you have there. Otherwise, the webinar will also be available on the Innovametric software channel on YouTube. Our next webinar is scheduled for October 10th, and we are going to talk about how to use PolyWorks Modeler Lite to optimize and measure polygonal models. So thank you for joining us this morning, and we'll see you next time. Bye-bye, everybody.